Bye guys, have a good day, have a good weekend.
Caitlin Woody, report to the sign-out office. Caitlin Woody, report to the front office. Teachers, please check your email about dismissal for the football team to get today early.
That envelope right there. This?
How about this elaborate to extra?
Hey, are you gonna send me that link? I've got it ready to go back to her again. Wednesday, again, get, I sent you a message back. As I just need to wait. I'm not being able to call. And I've got it updated email ready to go back to her.
What did you say? I was reading that top thing over. I was gonna email him quickly like, what's going on? What's part right again? Good shopping. You're running the part like you
Yes.
No, this is our last one. This is our last one. Really, our grades were actually coming out based off the weekend. Is there 18 more next time? No, probably not. Well, they got a bit national, so they're going national.
I don't know.
Todd, his biggest concern at practice last night was bringing baby chicks.
You wanted to bring him at the beginning of my practice.
But what do we got to do? All day long.
I would assume that. I would assume Ashley Fisher.
But they're not just gonna wait 2 months and go. Well, he said that,
We wanted to go to the Queen City and our parents had to organize and all that stuff. Yeah. So,
and I think you're only allowed to buy, we're only allowed to buy, all the space. That's all you need.
So we're going to senior parade on April 12th. Or, wait, we come back April 12th.
yeah, we're on the senior parade.
Oh, they were talking about like, you know, like on the first day of school, how we like worked in the hall together. They're trying to make it like.
So we're gonna like rewear all our senior shirts and
I
everything?
guess so. They're trying to make it like the first day of school. Yes.
That's cool.
Yeah.
Who said that?
Meredith and Deshaun and
Your council?
yeah.
Yeah.
They're trying to reach.
Okay, guys, let's go ahead and spit out our homework.
Oh my gosh, I switched my entire rotation this morning. It was amazing. And they got so mad at me and it worked. I put one of my outsides in the middle and then put my right side in my other middle and outside. And then put my favorite that ever played on the right side. And oh my god, it works.
What did you do to
She did. Cause she's like 5'2", but she can jump. But my other hoop, I should have done that from the beginning. Oh, so good. It is so good. And we're all like, we hate it.
And then Arden, the girl that she was so mad when I put her in, and then she started getting like really good swings, like, cause it makes her jump, cause she doesn't have a jump on the outside. And so they were going in and then they out, and she was like, she came out and she was like, oh, I kind of like that. And I was like, wait a minute, since you like this rotation, she's like, well, I'm gonna say no because no. I do this, we had a tournament for about 2 weeks ago. I was sitting here on Sunday, and they had to put red as outside. Well, she like had switched the whole rotation, so this is how she did it. She was gonna have red as an outside, and only have one middle. And we're just gonna be 17 minutes. Yeah, and they're on the but instead of doing all that, she just put it as an outside, and then just like ran like that, and have a little bit. So they didn't do that, they won. And then, we were just doing I did not hear what you said. After we just returned the which is long and those the issue was not working.
While we were there,
We got that.
Are you kidding? I bet Kat was not very happy.
She was, no, we didn't have practice Monday or Wednesday, so she doesn't cancel tomorrow's yet because we all feel wonderful. Like she didn't do, if we all hung out the whole day because we would have put 7, 8, and 9, but like she never hung out with us. She just didn't hang out.
That's good though, that she didn't have to. I got confused with some of these, but then most of them I understood.
See, what did you get for 71?
Y equals negative y ex plus cy over x dy plus
Oh my God, it's
That's what the ones I had questions on.
Callie, what are you talking about?
I don't know. That's the ones I had questions on. I think I have questions on 1, 2, 3, 4 of
That's
them.
right.
4 of them. Oh, and 5 of them, the first one.
Well, 71, I did it, and then I checked the back of the book, and it was like the same thing, except the positives and negatives were switched. I don't know that.
What did you get for 40 minutes?
3 times e to the negative t plus e to the t squared times e to the t plus e.
That's not what I got, but it's close. I have to go on my pack, and they're not leaving the front door until like 5:30. Because people are sold out and she's not.
Perhaps this will, shed a little light on your issues there, Cal.
Oh, wait, maybe you were right.
Let's see, 41. That's I think I got one right.
Yeah,
So,
what did you get
For
41?
41, if I left it,
71.
Mr. Coffee. On 41, like if that was a test question, and I left the e to the x to the 1/2, is that right? Or do
I believe I'd take that, yeah.
Okay.
Looking at these, if your notation is equivalent towards the end, I'll probably take it, to be honest.
That's L and X, right?
Oh,
On
wait.
45?
45?
Yeah.
After log
Because it
out.
doesn't have like the,
Yeah, I put it in like
Which one?
because that's the,
71.
that's the,
Sorry, which one?
That's 71.
70.
Yeah.
that's the derivative I got, but I thought it was asking for the actual tangent line.
Yeah. That's
It is, I forgot to do that part. The test, it looks like,
Yeah.
yep. Yep, looks like I just forgot to put that part in. But, I mean, from that point, you have your point, you plug in, you evaluate. You would read these down, and that will give you your slope, and then you already have your point, so you should be set.
I did not even know. I have a few questions.
Okay. Okay, let's get started. So if you have some questions.
Yeah.
So homework questions and any questions on quiz we need to talk about here today. Or quiz due tonight. Let's start with quiz. Any quiz questions we want to talk about? Anyone? Number 2, let's go ahead and pull up the quiz. Take a look at number 2. Okay, number 2, write the equation for the tangent line of the graph through this point, 2, -9. Okay, so what do we need to do this? What's the structure for this problem? What's our steps that we're going to do here? We need to do what, then what, then what.
Right, I figured it out, but when I went to graph it, it didn't.
Hmm.
Like it didn't actually.
Hmm. Well, let's double check here. First thing we would do, Fatima, is what? What'd you do? Okay, so what's our function again? We got natural log of, what is it, 3x, right?
Yeah, 3x.
3x minus 5 and then minus 9 on the outside. It's minus 9 on the outside. So, need to take the derivative. How are we going to do this? How are we going to do dy dx here? What's the derivative of the natural log? Okay, and then we'll multiply by what? Because that's the derivative of the interior, right? So we're looking at this. This is our dy dx, right? Okay, what are we plugging in here? It's positive 2, right? Just want to make sure, double check. Yeah, it is positive 2, so we'll plug in 2. And we're going to get 3 over 6 minus 1. So that's going to be 3 over 5, right? 3/5? No, just 3. Sorry. I'm having a mental meltdown. Just 3, right? Okay, so this should give us our equation of our tangent line, right? We're going to have y minus y1 equal to mx minus x1. We have all of this stuff, right? Okay, what's our y1 here? It's -9, right? So this is going to be plus 9. We just found this. It's 3 and x minus 2, correct? And you said when you graph it, it doesn't quite seem like it works. I'll have to double check into it. It should work. Let's double check. Let's bring up our best friend. Desmos, natural log 3x plus minus 1. And it certainly seem like they're raising off of each other right there. Right at the point that we're talking about, 2, -9. Have you typed it in wrong?
Well, I like songs over it. I like songs over it.
Seems like, man, I think we're on track there for that. Okay, so well, there's number 2. It shouldn't have worked it all the way out for you guys, but I was kind of curious to make sure that it worked. Other quiz questions we want to talk about?
Number 6.
Number 6, our very last one here. So we have the integral of e and e squared of 1 over x natural log x. So obviously you need to do the integral here. E squared 1 over x natural log x. What I recommend here is to split this into two fractions for us to do this integral. Where are you stuck specifically?
The integral of the ln x.
The integral of ln of x. Okay, so we have e squared 1 over x. We have 1 over natural log x, like this, correct? dx. So what did you do here?
I don't know, I really didn't even know where.
So here's what I would do, is I would do a little u substitution and say u is going to be the natural log of x. That makes the derivative of u what?
1 over x.
So I'm thinking that when I do some u substitution here, I'm looking at 1 over u then instead. Does that help you out a little bit? Okay. When you evaluate, you're definitely going to want to maybe use some power rules to help you. Any other questions we have? Concerns we have? Kayla said number 6 on the quiz, but we just took a look at that. Let's go ahead. Let's talk homework. Let's talk homework. What do we want to talk about with homework? 4.
37, 49, 65, 69, 71, and 99.
Okay, we're not doing all those. 37, 49, let's take a look at a few more. What were the other ones?
65, 71, and 99.
Yeah, we're probably not going to do all 5 of these, but we'll see. We'll see. Other problems that we want to take a look at? 109. Okay. We'll go ahead, we'll take a look at 37. We'll go ahead, we'll take a look at 37. We will find the equation of the tangent line to the graph given here at point 0, 1. So very similar to the question that Fatima, you asked earlier about the quiz. We have our function y equal to e to the 3x. So we need to find the derivative of this function. How are we going to do that here? What's the derivative of, we'll use substitution. I mean, I don't really think I have to do the full sub here. You guys should be able to do it mentally at this point. What is it? What's the derivative? 3e to the 3x. Right? Okay, what point are we plugging in? 0, 1, right? Okay, so 0 goes in, so when I evaluate this at 0, I'm going to get 3 because e to the 0 power will be 1. 1 times 3, of course, 3. Okay, this gives me everything I need to set up my my line here. Y minus 1 equal to 3x minus 0. That's it. That's all there is to it. It's a very straightforward question. We will take a look at number 49 as well. Take a look at number 49 as well. Find the derivatives here. So for number 49, we have g of t equal to quantity e to the negative t plus e t all to the third. Okay. So, how should we approach this? How should we approach this? It's just a standard chain rule. It's just going to be a standard chain rule here. If you want, you can simplify it a little bit. You could use sub a little bit, but it's not fully necessary. We're going to take this power down, make our new multiplier e to the negative t plus et. That's going to be the squared now, and then the derivative of what's inside. So the derivative of the first term is just going to be negative e to the negative t. And the second term is just e to the t. There it is. The reason why the second set there, the one I have in brown, why it's a negative e to the negative t, is because once again, the chain rule, the derivative of the top there, derivative of negative t is negative 1. So rather than multiplying just by a standard one, here you do have to bring in the negative 1. Questions for this one? These are not super difficult questions. $65 is basically the same thing as what we just talked about. The only issue there is it's a more complicated derivative to do. I think I'm going to skip past that one for the time being, just because I don't want to get into all the different products and things that I have to do. If you want, I can just scroll down here. You can see the work that I've done. But if I have to imagine that we made a mistake, I have to imagine that mistake happened while doing this derivative right here. It's not a friendly looking derivative. I would give you this one as 65 is a tough question. It's not inherently on its merits, but more just because it's a challenging derivative to get. But it's no different than the other two that I've done today. Find the derivative, plug in your point, and reduce down. Your derivative here, when it's all said and done, will should reduce down to just be x squared ex. Expands out pretty far, but a lot of those terms end up coming back together. So that's 65. Like I said, I'm not going to go through it in its entirety there. We'll look at 71. It's really no different either. Just once again, this one for 71, you have a little implicit differentiation here. So that's what we talked about earlier when you guys asked, what aren't you supposed to? Yeah, I am. So how we would approach 71, obviously I have the derivative worked out there on the answer key. So we'll do the implicit differentiation. Let's throw it up here real quick though, just for us to see. We have x ey plus y ex. So these are both product rules. When we're done with, it's all said and done with, these are both going to be product rules. This first product rule, it's going to be ey plus x ey dy dx plus dy dx ex, and then plus y ex. But you can keep going and do some factoring and do all the other stuff. But you want to isolate this singular dy dx. You want to isolate this. So when it all reduces down, we're going to dy dx equal to, where's that over there? It's negative ey minus y ex. Try to focus cell in correctly. I can't read it because there's a massive glare on the screen here today. Negative ey. And then, of course, we'll go ahead and we'll have a denominator, which is x ey plus dx. x dy plus dx. So this is ultimately what our derivative ends up being, right? So I have a point here to plug in. So the only difference here with this one as opposed to the previous ones is you do need to plug in both your x and y values. Fortunately, I gave those to you, so when you plug this one in, to find dy dx, e to the negative 1, make sure I plug in the right values, s1 minus 1 e to the 0 all over 0 e to the 1 plus e to the 0. A lot of this is going to simplify down pretty easily. We're looking at all this becomes a negative 1. This is e to the negative first. We have e to the first down here plus 1. If you want, you can bring that e down if you really want, or you can force another fraction there, but this is what we're looking at. You can actually keep working this if you want. You can make this into a common denominator across the top. That would be 1 over e minus e over e, which would be 1 minus e all over e. And then you have, of course, your denominator, e plus 1 times e plus 1. So you're left with 1 minus e over e times e plus 1. If you wanted to get to a singular term here for your slope. Questions? And then, of course, it's just the point slope form. 71, 99. 99 and 109, they are in the same section, unless there's something massively different about them. I think I'll probably only do one, so that way we can get into what we're going to do today. I'm probably going to skip over 99 because that's a super easy u substitution problem. You're going to set u equal to 5x. You set u equal to 5x, that makes your du 5 dx. That's pretty simple, straightforward u substitution problem there. We'll look at 109. I think 109 is a little bit more challenging, so I think we'll look at that one. 109, we have the integral of e to the x root 1 minus e to the x dx. We're going to use u substitution here for this. U is going to be 1 minus e to the x. That makes du negative e to the x dx. So that's what I'm going to need to bring in here. So it's a negative and a negative on the outside. So we're looking at negative square root u du when we do our sum. This will be negative square root, or not square root, u to the 1/2 du. We can integrate this pretty easily. This is going to become 3/2 over u to the 3/2, of course, with the negative on the outside and plus c, or negative 2/3 square root of u cubed plus c. Let's go back to what we have. We have negative 2/3 square root of 1 minus e to the x to the 3rd power plus c. Questions here for this one? Concerns here for this one? Okay. Well, we're effectively down a half-hour class here or so, but that's not that bad. All honest, I'd rather us be all on the same page, especially with a lesson like today, where today's lesson is mainly just practicing. Very similar to what we did yesterday. I'm going to show you some new rules, some new ways to do derivatives and integrals today for logarithms that are not natural logs, so anything that's not e or natural log. We'll talk about those today, and then we're just going to practice those in kind of all different settings. So very similar to what we did yesterday, or at least yesterday's lesson in procedural kind of mindset. Let's go ahead. Let's get into things here. Let's get into our lesson today. Talking about logs with bases other than E. Okay, so let's jump into this here. Let's jump into this. Starting on slide 2 is some basics about logs and how we use logs and exponentials. So a number that we use as the base, if we set that equal to the log base, those two will cancel. In other words, by log base 2 of 2, those cancel and I'm left with whatever my exponent's going to be. Likewise, this works in reverse too. If I have 2 to the log base of 2, let's say x, those will cancel, and once again, I'm just left with what's behind. That's what we see here on our second slide. Basic property of where logs come in. This is the same deal as it was with natural logs. It's just instead of using E, we're using any number in any log base. What you see up there, that IFF, that is math notation shorthand for if and only if. If and only if. So that's, of course, y equal to ax. That's the standard set for our exponential functions. So if we wanted to convert that to a logarithm, that would be log base a of y equal x. So that's kind of what happens there. You guys might remember from pre-calc, the logs be so easy. That was like unit 2 or 4 or something like that that we did together. We should be relatively comfortable with a lot of these rules today. Questions here? Okay, so just to prove a point here, let's go on to slide 3. Can you help me solve these ones? Let's use some logs. Let's use some exponentials to help us solve these ones. Let's do the first one with the logarithm. Oh my God. Okay, let's solve this first one with a log. I said all my markers down. I have no idea what the second one. What should we do? If I want to solve that with the log, what should we do? If I want to convert it over to a logarithmic form, what's it look like?
Log base 3 of 1 over 27 equals x.
Log base 3 of 1 over 27 will all be equal to x. Now, if you have a nice calculator, and most of you do, you can punch this right in. Most of your calculators can do the change of base without actually having to do it. If not, you can always use change of base formula and convert these to common logs. Log over 127 and log over 3, all equal to x. So either one will work. Should get -3 as our answer. Questions here? Okay, let's look at the other one. Let's solve the other one using an exponential. So log base 2 of x equal to -4. How do I convert this back to an exponential? What's the base? What's the exponent? What's my solution?
X equals 2 and -4.
X equal, base here will be 2, the exponent of that 2 is -4, and x will be equal to that, right? Which is? I heard somebody whispered more than once. 16. 1 over 16. Questions here? concerns here. So we'll use these rules and these kind of tricks to help us set up our derivatives and integrals. Generally speaking, it's pretty helpful to be able to convert one to the other. Okay? Let's go on to our next slide here and take a look at these different rules here. So here's some basic rules for us. So some derivative rules of logs and exponentials. So let's start with the first two, which are for exponentials. The derivative of a generic exponential, a to the x, will just be natural log a times ax. Reality is that we'll probably use number 2 way more often, which is the u substitution version of this rule, which is the natural log of the base times the subversion times the derivative of that u substitution. This is actually the same rule as it was yesterday and the days that we had leading up to yesterday, going back to even where we started this unit with the derivatives of natural logs and things like that. We talked yesterday about e to the x, right? So according to this, that would be natural log e times e to the x, right? Well, natural log e is just 1 times e to the x. Now you see where we get that from, right? We talked about that yesterday as well, right? So that's kind of what we're looking at here. We'll definitely use number 2 way more than we will number 1, but every once in a while we'll use that first one to kind of help us simplify the problem. Let's look at 3 and 4. Those, of course, are rules for logarithms. So the derivative of a standard log with base of a of x will just be 1 over the natural log of a, that base, times the value of x. It is important to note that x is not inside that natural log, that x is a multiplier to that natural log. This follows a similar principle when we use the u substitution. If I have log base a of u, it'll be the same natural log of a times the u times the derivative of said u. Questions here? All right. Well, then let's move on here and let's do a little bit of practice. Let's do a little bit of practice here. Let's start with slide 5. Let's just find the derivative here, y equal to 2x. Y equal to 2x. 2 to the x. What's that going to give us for our dy dx? It should be an easy problem. Who wants to do it? Adam, what's this going to be? Dy dx is going to convert over to what? Natural log of 2 times 2 to the x. Questions here? Concerns here? Okay, let's move on to the next slide then. Let's move on to the next slide, the next problem. We should be on slide 6 now. Let's find the derivative here. I got y equal to the square root of x. Y 2 to the square root x, like so. Okay? What's help us out here?
Natural log of 2, or, natural log of 2 times 2 to the square root of x times 1 over 2 square root of x.
Okay, now how'd you get that?
You set square root of x and you use substitution.
So that makes du, or as we've been using it here, maybe not du, we should use prime, right? That makes this 1/2 x to the negative 1/2, correct? Or 1 over 2 root x, like so, correct? So using that to help us out, the natural log of 2 times the original function, 2 to the square root x, right? Times the derivative of that exponent, which is 1 over 2 root x. The only thing here is that we might want to put this all into one fraction. So on top we got natural log 2 times 2 square root x all over 2 root x. Questions here about this one? Concerns here for this one? So I think this problem really shows and showcases something that's very important. Something that we should probably talk about, which is why I think we struggled with our Unit 4 test and why we've struggled with a couple other things. We've reached a point in calculus where it should be second nature for you to do more common or easier derivatives and integrals. Things like what we did in Unit 2 and in Unit 3 should be not really anything challenging to you guys anymore. This derivative here, for example, u2 equal to root x. We've done this hundreds of times, and that's not an exaggeration. It pops up very frequently in our problems. We shouldn't be making mistakes with this anymore to do this. That's part of what's the issue here is some of us never really learned some of those basics for whatever reason. Whether we were using outside sources to do the basic ones, the easy ones, whether it was I didn't understand the lessons, whatever that might have been, we don't have that. Some of us are really weak in that basic level skill set, those foundational things that I said in Unit 2, Unit 3. You have to know this. You have to be good at these before we can move on. And that showcases in Unit 4 when we start doing those in reverse. If you can't do them forward, you most certainly can't do them backward as integrals. And now we're going to see as these start to stack up, as we start to put more derivatives inside derivatives, we start calling on multiple functions at a time, which is what this unit has been about so far, we're going to have issues. Questions here? I think the important thing is that if you find yourself struggling to execute even problems like this, if you have trouble with getting this out correctly and getting your math correctly here, my advice to you would be go back and practice your basic derivatives, your foundational pieces of derivatives. Go back to Unit 2, go back to Unit 3, and work on the very basics of derivatives. Let's move on to the next one here. Next slide, next problem. We're looking at y equal to 3 to the 2t all over t.
Our purchase email was sent straight to Holly with the directions of go forward with these purchases. I'm not sure what's going on, but that included the 2 sets of calculators and your GIM.
Well,
So
I should have asked for a $30,000 bonus then. I might have just gotten it with no questions asked.
you might have, but now, the GIM kit, I may have to have you get it and be reimbursed because it's gotta be linked to a teacher's account. So I don't know if Holly can do it that way, but we're getting everything on the list.
Well, there we go. All right, gang. What are we thinking here for this particular problem? What do you think we need to do? We'll all everybody volunteer at one time. Quotient rule, I think is a good place to start. Quotient rule is going to be a good place to start. We'll call this our function f and our function g, right? G derivative, very easy, that's going to be 1. F's derivative is going to be what? Three to the 2t, right? Times 2, right? So really, if you want to look at it this way, you could make this the natural log of 9 times 3 to the 2t. So what you can do there is you move that 2 to the front of the natural log. Now it becomes a power rule. You can bring that up to be the power of 3, and 3 squared is 9. That does help you reduce this down a little bit. You don't have to do it that way. It might not be beneficial to do it that way. We need to see what's going to happen when we actually set up our full quotient rule to see what's the best way to go about this. So let's set this up here. Of course, on the bottom, we're going to have t squared. We're going to have g times f prime. So that's t times, or let's go with the natural log 9 times 3 to the 2t. Minus f g prime. Well, that's easy. That's just 3 to the 2t, right? Everybody good with how we started this out so far? Taking a look at my work here. I didn't put the 2 up right away. I actually left it down on the slides. When I look at this, there are some things we can do here. I can go ahead and factor some stuff out. And right here, I can factor this out. I can make this 3 to the 2t times t, natural log of 9 minus 1 all over t squared. I could actually represent this another way. Of course, I can use what's on the board, where that 2t is back down. I can even go one step farther. This is equivalent to 3 to the 2t over t squared. And this could just be natural log of 9 to the t minus 1. You can, of course, do that too. So this one, and the one on the board are all equivalent. It's all just where we want to express that 2t. Do we want to express it as a multiplier in front of our natural log, as a power, as a simplified power? All of them are pretty much equivalent here. This unit requires a lot more from me as the teacher to grade it than it really should require from you guys to do it. Questions here? Okay, let's jump on to another problem. Let's move forward then. Next slide. Let's do one with some logs. I've done all exponentials. Let's go back and let's do the logs. Do I have to specify that this is log base 10? No, I could have just technically just wrote log up here, right? Because the common log like this is assumed to be log base 10, right? Let's tackle this one. Let's tackle this one. Shouldn't take us very long. We're just about done with it. What do we need to do? Some u sub for cosine of x, I assume. What's the derivative of cosine? Of course, that's negative sine, right? Right? Okay, so this becomes log base 10 of u, which allows us to do the derivatives of dy dx. This becomes what? 1 over what? Times cosine of x times the derivative of that, which is negative sine x, right? So we get to this step here. Are we all good to this step here? Okay, we can do some simplifying here. Can do some reducing here. Let's put it back into one giant fraction here. This becomes negative sine x natural log of 10 times cosine x. You can actually split this into negative natural log 10 and tangent of x. Sine over cosine is tangent. You could, of course, leave that as one cohesive fraction, negative tangent of x over natural log 10. Questions here? Concerns here? Okay. Move on. Next slide. Slide number 9. So, slide number 9, I'm going to introduce to you. We did derivatives all the way up to this point, so let's talk about an integral. Let's talk about integral. So, the integral of a standard exponential function, the integral of a standard exponential function is going to be equal to 1 over the natural log of its base times the original ax, times the original exponential. This works best if we start by defining what the base of our function is, what the base of our exponential is. That should be clear, and I highly recommend that you do that first. You can do u substitution along with that at that point, but I think it's very important that you clearly define what your base is. That way you know exactly where we're going to put our u substitution and where we won't. Questions here? Let's move on from slide 9. Oh, let's do a quick problem. Let's do a real basic one. We have the integral of 2x dx. So when I set this up here, obviously a is going to be 2, yes? So this will be 1 over the natural log of 2 times 2 to the x, or 2 to the x over natural log to all plus c. All plus c. Questions here about this one. This is actually the same rule that you can use for natural or for E that we talked about yesterday. And you could show that very easily because you'll end up with 1 over natural log E, which is then 1 over 1, which gives us back EX. Let's go ahead. Let's move on from slide 9 now. Now that we did a basic one, let's do a more complicated looking one like this one here on slide 10. Which one of you guys in here want to help me with slide 10? I'll take the reins, but I'm going to need some backup. Who wants to help? But you guys aren't helpful. Jake, help me out. I haven't heard from you really today. I got 7. 3 minus x quantity squared dx. Okay, so Jake, clearly we're going to want to use some u substitution here. I think it's best if we define what our base of our exponential is when we define our u substitution. So what do you want to do first? Define u or define a?
A.
Okay, what's a?
7.
A is very clearly 7. Okay, so what are we going to set u equal to then?
3 minus x.
We're going to set it more than just 3 minus x. We're going to set it equal to that whole group 3 minus x quantity squared. That way when I go for du, that becomes 2 3 minus x dx, which I see I already have that. I just need to bring in the right multiplier, correct? So I'll bring in the 2 inside, so that means the 1/2 outside. If I want to rewrite this in that format, we'll have 1/2. We'll have the integral 7 to the u du. Is everybody okay with our substitution and our setup here? I think this one is not super difficult. This is actually one of the easier ones to see what your a value is supposed to be. But I think you could see where it's easy to make this more difficult. For example, if I distribute this 7 through and don't have that group out front and make it all into one giant messy looking equation, it might be a lot harder to see that. If I have 21 or 3 times 7, if I have to do factoring here, if I got to do all those other things, it can be a lot more difficult to see this common base here. Pardon?
Like for the u substitution, do you multiply by the inside?
Yes, it should be -2. Thanks, Fatima. I forgot about that. This should be a -2 and a -1/2. My fault. My fault. My fault. My fault. Okay. Let's keep up with our work here on our slide here. So we started by defining a. We defined u. We got du. We did our coefficients brought in. Fatima caught a small mistake there that I made. Thank you, miss. And now we have it set up ready for our actual integral. So Jake, let's actually do the integral here. What would be the integral of 7u?
1 over ln.
Natural log of 7, right?
Yep.
Times. Let's just keep it as u right now.
7u.
7u times.
Oh wait.
Yeah, I think we've made a mistake already.
Why is the 7? Wouldn't the 7u be up?
Not quite.
Like on it by its own?
Let's go back, Jake. Let's go back to slide or 2. Let's go double check our rule. We seem like we're a little shaky on it right now. Okay, so we have just this, right? So it should become natural log of 7, right? Which is what you got. It will be multiplied. So yes, that should be, maybe not necessarily up, but outside of the vector log, right? The times 7u, correct? And then according to that, we need anything else?
C.
C? Okay, let's go double check our work here, Jake. We're integrating this wonderful looking mess. I think everything looks good here. The only thing I want to do is I want to go back to our x values here. So we're going to have negative natural log 7, right? I actually don't really need this one up here. This is going to become 7. And this is going to become u again, 3 minus x quantity squared. All plus c. Questions here? So on the board, I left a lot of those things separated. I didn't put them all into one fraction. For this one, on the TV, on the slides, I left it as, you know, obviously as a fraction or not fully multiplied out. This one I did. Questions here? There's a lot of moving parts here. There's a lot of pieces. I don't think the concept is exceedingly difficult, but I do think that it is easy to get twisted up in your work. Let's move on to the next slide. Next slide, next example here. We're on slide number 11. Can you find the integral here? Can you find the integral here? Why don't you guys do this one without me, and we'll see how we do. This was natural log of x times the original explanation. We're not doing the rate with your circle.
Oh, that's a good reason why it's not working.
You did the integral here, and now you're trying to do the derivative on the other side. All right, guys, what do we want to do? What do we want to do? Let's know, what do you want to do? Not up? Got no ideas whatsoever?
I get confused on what the set U equals
All right, well, first, I'm going to tell you, I think we should split this up. I think we should split this into two separate integrals. Because this one will be easy, right? Should. This one, this is where you're saying you're having a little bit of trouble, right? Let's do this one first. That's going to be what? X to the what over what? Don't overcomplicate this first part. Do the integral of the power rule, right? We're going to add 1 to the exponent, correct? X to the 4th. We're going to divide by the new exponent of 4. Okay? Plus this one. So you said you had some trouble figuring out what u is. I'm going to set u equal to negative x. That makes du negative dx. I need to bring in some negatives here. Negative on the outside, negative inside. Okay? This becomes negative 3u du, which becomes negative natural log of our base 3 times our original 3u, or negative x. Let's check out our work so far. So I set u equal to negative x. I split it up. I did my multiply, and this is where we're at so far. I don't really see too much that I can really put together here, other than maybe just make these into cohesive fractions. I can make this into, well, this is a cohesive fraction here, x to the 4th over 4. And then minus natural log 3 on the bottom and 3 negative x on the top. Plus c. Questions? Concerns about this one? Your silence is unnerving, gang. I know there's not many of you in here today, but your silence is a little unnerving. I don't know if we're doing well, if we're not doing well. We talked about this yesterday. If we're struggling, you got to speak up. I don't know what to do for you. Are we doing okay? Does it make sense? Is it an alien language? What do we got going on here? Some feedback, please. Thank you, Jake. Jake says he's good. Bianca says she's good. Awesome. Okay, well, I guess 2 is better than none. Thank you. Okay, move on. Just do another one. Let's start mixing and matching up here. Next slide, next problem. Y equal to the 2x minus 1. Can you do the derivative here? You guys are making classes grind so slowly right now. I don't know if it's just because we're not comfortable with what we're doing. What the issue is. That's it. Good? Sure. Oh. I'm freezing the screen. Okay, here's our answer. Here's our answer. 2 natural log 7 times 7 to x minus 1. Questions here? Pretty straightforward, just went back to what we were doing earlier, right? All right, let's move forward then. Last problem of the day. Last problem of the day. Can you do the derivative of this? Okay, you guys look done. So who wants to do it? Who wants to help us wrap up for today? All right, Bianca, go ahead. What do we got to do?
So I set A equal to 3, and then U equal to x squared minus 3x, which is U prime 2x minus 3.
Okay, so when we swap this over, log base 3 of u, correct? Okay, the dy dx derivative here.
Is 1 over natural log 3 times U times the derivative.
U prime, right? Okay, and now all we need to do is convert back to x. So this would be 1 over natural log 3 times the group x squared minus 3x, correct? And on top, instead of 1, we'll put the derivative to 2x minus 3. Are we all comfortable here? All set. Everything here looks good. There's nothing more to reduce, although it is tempting to factor out an x on that bottom to see. We should know better than to think that that's going to reduce. That's it for today. That's all I've got. That's all I got. Homework is on the last slide, page 368. Go ahead, get to it, or use this time to work on your quiz. The choice is yours. We got about 10 minutes or so.